This is a quick video compared to the others for the 31st of March because we just did the last part of, well, in class we did other stuff. A whole lot of me running around trying to make Zoom and connections work to no avail and told the end of the class and all that, so it was that crazy class. And the first half of it we spent, just for the people who weren't there, so they know, we went over without ability for projection up on the screen, just me standing there reading through each one of these and getting everybody to try to figure out how best to define them. And some pretty good definitions, I would say they were. So that's a good exercise for sure in preparation for tests in the exam, but I mean there's a whole lot more, mainly focusing in on the 4 challenges. So back to that. Challenge 4, we had done the first half of it way back in the beginning, because it is understanding the advantages and disadvantages of genetic algorithms with respect to other approaches. So you'll recall that we went through 5 classes ago, it would have been, I guess, brute force, mathematical approaches, other heuristics like ant colony, nearest neighbor, and two-op swap. So then the remainder of the class was the list of advantages of genetic algorithms and disadvantages. First thing to note is that the first 4 come directly from the discussion. And here's a copy and paste of that discussion. Remember, the discussion appears just before the challenge is faced, and it just has all these terms. But it starts by saying the advantages of genetic algorithms are thought to be, etc. And so really, if you do get this question on a test or an exam, then you can kind of use this as the first half anyway of the advantages and just show that you know what each of them are. And so here they are, one after another. And I guess what I've done there is trying to remember why I colored these. And so these are the advantages in green, and then the disadvantages are in red. So number 1, if they work well with a large fitness landscape, large problem space. In other words, it really doesn't matter how big the problem space is, because we're not relying on mathematical linear or brute force approaches where they take a certain amount of time. We're going to run the heuristic for a while, and we're going to have an optimum, and we'll be hopefully happy with that. So yeah, the fitness landscape is really not, in terms of its breadth and its size, really not limited. 2, their randomness helps avoid local optima and therefore suboptimal solutions. This is going back to the last video, this whole idea of convergence and how we don't want early convergence to suboptimal solutions. And we're always going to have a what's your definition of optimal? Optimal in the case of heuristics is really pretty good, really quite good, not perfect, but really quite good, rather than kind of ho-hum, could have been better. And the way that we don't end up with ho-hum, could have been better, is through randomness. And randomness is achieved through various things that you would have read about and thought about and we've talked about. Stochastic universal sampling, for example. This whole idea of exploration and novelty searches and so on and so on and so on. And so whatever else is said here, the fact of the matter is that we do use randomness, and that randomness helps avoid coming to an early suboptimal solution. 3, there is a natural balance between exploration, which is very much connected to the randomness, and exploitation. Remembering that exploitation is crossover. Crossover is exploitation in this case. We're exploiting the fact that the parents have good genes, and we're crossing them over with each other to get even, hopefully, in some instances, better genes. That's exploiting the crossover function of natural selection. But there's a balance between that, taking the good stuff, taking the good genes, and exploration to genes which may not seem so good, but, and I'm saying genes, I probably should be saying chromosomes. Genes will be part of those chromosomes that we explore, these ones that are not obviously good, but as we've seen many times before, I've shown that diagram of not so good and not so good together can, in some circumstances, make really good. So there's a balance between the exploration and the randomness and the downright, let's do what natural selection does generation after generation with the crossover. Of course, I just need to add there that don't forget that natural selection does employ mutation as well, which is obviously more exploration. So they explore even further through novelty searches. So there's exploration by throwing in mutations, but we have even these directed, not just mutations and see what we end up with, but actual directed novelty searches. So we're like, okay, we're not going to go the direction that seems most obvious. We're purposefully going to go over there or over there and try these different routes just to see. And hopefully 1 out of every 1,000 or 1 out of every 100 or whatever ends up yielding something that's very useful to our evolution of our genetic algorithm. And then the last, are there 4 of them? 1, 2, 3, 4, 5, I guess, are not from the discussion, but they're things that you should, well, how can I put it? They should seem kind of obvious to you, but maybe not. The concept is easy to understand, given that you learn natural selection in grade 9 or whatever. It's not that hard to understand. So this idea of generation after generation getting better and better, pretty easy concept to grasp. We're able to find an answer fairly quickly. We don't find the definitive answer, unless we're just totally lucky, but we find an answer. We find an optimal answer fairly quickly. With the genetic algorithms program that we've got that we've been using, it's a matter of seconds, just a few seconds. They do work on a wide variety of problems. That's not anything that necessarily has come up before, because we keep on talking about the traveling salesman problem, but there are lots of problems that are related to the traveling salesman problem, and there are other problems as well for which there's no computationally easy solution that they can be applied to. So there you go, that is true. The coding is relatively easy, this compared to some of the mathematical type of approaches. So you may or may not agree with that, but on the grand scheme of things, they really are easy enough to follow. And they are inherently parallel. That's one that I went to the board, and I don't have my iPad hooked up here, but you just imagine a quad-core computer. It's got these 4 cores. Well, it can take any one particular generation, and one core takes 1/4 of the crossovers, and then the next core takes the 2nd quarter of the crossovers, and so on. And so since there's just a bunch of stuff that can be done at the same time, they don't have to be done sequentially, these crossovers. They can be done at the same time. You can have 4 being done at the same time. So the way that it works is inherently parallel, which obviously speeds up processing. So then there are a few more that I've kept on coming across, and I kind of understand them, but I kind of don't, so I'm not going to dwell on those. Well, I mean, number 10 I get, but I'm not quite so sure what these 2 are about. And then the disadvantages. They don't find the definitive answer. The only thing that finds the definitive answer usually is brute force, but again, we just can't do brute force in some problem cases. So, but just, it's worth noting that we are not finding the definitive answer. Getting the design right is difficult. To design a new genetic algorithm, as is getting the parameters that you're going to send that genetic algorithm. So a little bit tricky both with how you create your, I say the coding's easy, but understanding what you want to do sometimes isn't the easiest. And so a lot of trial and error, and definitely a lot of trial and error with figuring out the ideal parameters. And there are a bunch of them. I've got some down here, the crossover rate, mutation rate. So, you just take your time and you change the elitism value. The thing is that they affect each other. So you just can't change one and say that this is a perfect number, because it might not be a perfect number when you change one of these other numbers. So there is quite a bit of tweaking, and like it says someplace, it's a matter of feel after a while. You just get used to the way your particular algorithm works, and you just have a feeling that 150 this time is going to be good for the population. size, and a mutation rate of 0.06 is actually going to be better than 0.05, etc. So finding the ideal parameters is difficult. It's not so much that, well, I don't know if you want to call it difficult or just time consuming. And so 4 kind of reflects or summarizes both 2 and 3, that genetic algorithms compared to a lot of other algorithms are more art than they are science, which is rather ironic given that it's based on natural selection, but there is an art to it, employing trial and error as these two, speak to. And then finally, which is kind of interesting because we say that they do operate fairly quickly, but they can be a little computationally expensive compared to, I don't know, just a simple program, a simple database with not that many records, and you want to sort it or whatever. You're doing a little bit more computation than that. So that could be argued, I think, both ways, and so it's not the strongest of the disadvantages. But basically there are 2. As I go through this for the last time, there really are 2 main disadvantages. One is that you don't get the definitive answer, and 2 is that it's a tweak. It's a thing that needs tweaking as you run it. But dividing that up into 4 or 5 would be good. And that's it. That is the last part of the last challenge of this case study on genetic algorithms.